Hello dear, welcome our third lesson in this series. In this video, we are going to learn some important points about semiconductors, and these points are covered. The atomic structure of silicon is in the last lecture. Follow the link given in the description. Semiconductors like silicon and germanium gained its popularity for various reasons. Be manufactured to a very high level of purity with recent advanced technologies. The impurity level can be kept as low as 1 in a million. Second reason is, both silicon and germanium has very definite pattern, that is periodic in nature. Addition of impurity of proper type, that is trivalent or pentavalent atoms in the ratio of the order of 1 in a million, result in drastic change in electrical conductivity. The third essential property is sensitivity towards heat and light. Free carriers such as electrons and holes can be generated through the application of heat and light. This property is very important in heat and light sensitive applications, for example, laser soldering, photodiodes, solar cells, etc. Now, let's come to an important topic, that what are intrinsic and extrinsic semiconductors. Intrinsic semiconductors are those materials that have been refined to reduce the impurities to a very low level. Each atom of germanium silicon shares one electron with its neighboring atom. Thus covalent bond is made. So, there is no free electron in germanium and silicon. For this reason there is no conduction of electricity in them. Such pure semiconductors are known as intrinsic semiconductors. If pure semiconductors are heated at high temperature due to thermal agitation, electrons of pure semiconductors becomes free by breaking the bonds. Extrinsic semiconductors are those which is doped at a definite proportion to change its property, making it suitable for electronic applications, such as diode, transistor, etc., and optoelectronic applications, such as light emitter or detector. Let us start with N-type semiconductor. Figure 3.1 shows the crystal structure of an N-type semiconductor with a pentavalent impurity antimony. Antimony has 5 valence electrons, same as arsenic and phosphorus in the outer cell. We see that the 4 covalent bonds are still present, but the 5th electron from antimony is unassociated with any covalent bonds. This remaining electron is loosely bound to its parent atom, and relatively free to move within the material. Diffused impurities with 5 valence electrons are called donor atoms. A p-type semiconductor is obtained by adding trivalent impurities, such as boron, gallium and indium. Trivalent impurity has 3 valence band electrons. So, in this case, insufficient electrons to complete the covalent bonds of the newly formed lattice. The following table shows the comparison between N-type and p-type semiconductor.